Sleep and study. Don't forget to subscribe.
So here, talking about the dawn of creation, the first 2 billion years of the universe, it's my pleasure and privilege to present Dr. Stephen Beckwith. I moved to California 14 months ago, so I'm a native. People stop me on the streets. I tell them what the culture's like. It's good. It's easy transplant. As you know, I lived here 35 years ago. As Andy said, I graduated from Caltech. I just met another Caltech grad, 1948. Little difference, not much. But now I'm in Northern California. It's really pretty amazing. And I'm really honored to be here at this beautiful venue. Most of you in the audience, since this is the Silicon Valley lecture series, probably do things which are quite useful. So tonight you get to see someone who's made his career doing things which have no demonstrable application. In fact, I can almost assure you that almost everything I've done up until I became a vice president had no use whatsoever. But it's still interesting. And it's interesting because it actually ties us together and goes back a long time. I hope that's why many of you are here. You see my little collage of things includes this very old picture of a monk kind of reading a book. And it's meant, I use the word creation very purposefully here, because every civilization, every society that we know, from Aboriginal tribes to even, the more advanced civilizations of the West and East, have creation stories. Creation stories are among the most important things we have. They give our lives meaning. We've, as a species, I don't know if we're unique this way, but at least we believe we're unique in being the species that is so self-aware that we worry about where we came from, where we're going, what it all means. And so, despite this story having no real application, it nevertheless is the single thing that probably ties all civilizations together. So our forefathers and mothers did not play with computers and have silicon chips. They didn't have the technology, but they all had the same kind of creation story. Now, what's remarkable about our creation story is the creation story I'm going to tell you is based on modern science. And with modern instruments, in fact, even before we had very modern instruments, we were able to piece together the history of the universe going back quite a long ways. In fact, more or less 14 billion years. And what's amazing to me, I didn't even imagine this when I got my PhD. I didn't really imagine that we would be able to obtain as much information as we did. But now we are pretty confident that we understand in rough terms, and in some cases in very precise terms, what the universe was doing from a few milliseconds after the Big Bang until now. Now, and I'll make some grand claims, and I'll show you some data to underpin those claims. But the other thing that's interesting is with the Hubble Space Telescope, where I had a few years to play with it. We have the ability to look back and actually see things. So tonight, what I'm going to do is talk to you about the creation story, partly in honor of Andy, because this is a teaching college. We are going to have a teaching moment, and I'll teach you a little bit, I hope. But then I'm going to show you some pictures and show you that we can actually look back at slices of the universe at early times, and we can see what the universe was like before all of this came to pass. And so that's the arc of the talk. That's the creation story. Let me ask a few questions. So how many, maybe I get just I think if I step back out of it. No, there's no escape. Well, no, I just want to see the audience for a second, because just as you did, I'll ask for some, I see you're good at raising your hand. So how many people here raise your hand if you know about the Big Bang? Great, okay. Keep your hand up if you feel you could explain it to your siblings or children with some accuracy. Okay, that's good. How many people have heard of dark matter? How many people can tell me what it is? Well, fools for your paper. Okay, we won't go to dark energy. I already know the answer. Actually, you guys are pretty good. We could turn this into a revival meeting halfway through if you look for it. All right, so I'm going to talk about these things. Now,
all of you have heard about the Big Bang, and a lot of you know a lot about it. So those who do, bear with me a little in case you get bored. But what I want to do is set the underpinnings for my story. So to do that, I've got to kind of take you back to where this all started. And that wasn't that long ago. It was only about 100 years ago, about a century ago. And it started actually with a telescope in California. And that's that telescope on the right. That's the 100-inch Hooker telescope. It's on Mount Wilson, California. Mount Wilson is up behind Caltech in the San Gabriel Mountains. And, I did my thesis on that telescope, actually. They don't use it anymore. I guess after I got there, they shut it down. You know, good. That's Edwin Hubble on the right. He really did look like that. He really did. In those days, astronomers observed, you know, like this with suits and ties. Nowadays, it's changed. But it was all very formal. And what Hubble did with this telescope was really kind of remarkable. So I'll just set the stage. In 1918, say, 1919, we saw lots of nebula out there that we now know are galaxies, but astronomers that studied them had no idea how far away they were. They didn't know if the Milky Way was the whole universe, I mean, just our galaxy was it, or if there was something beyond that. A great debate raged. With that telescope, Edwin Hubble, in, I think, 1923, was able to measure the distance to some of these nebula, the nearest galaxies, in particular the Andromeda Galaxy, one of our closest neighbors, and prove that it was outside the Milky Way. And suddenly, all of a sudden, we understood that the universe itself was enormous. It wasn't just the size of the Milky Way, but it was just absolutely enormous. And I'll get to some distances in a minute. So then in 1929, he made a series of measurements, which you're going to see in the next slide. What he did is he looked at these nebula. He knew they were outside the Milky Way. And he measured the velocity. That's pretty easy to do. You can take a spectrum of a galaxy and you measure the Doppler shift. It's exactly the same technology, more or less, that the police use to give you speeding tickets on 280, okay? But you can do that with galaxies and measure them very well. That's the velocity. And then he measured the distance to the galaxies, and he didn't do that very well, as you'll see in a minute. But he made this brilliant plot of velocity versus distance, and he drew a line on it. And that line purports to show a linear relationship between the velocity and the distance, which is called Hubble's law. Okay? Now, you have to think about this a little bit, but it's exactly, if you sit in the middle, if you ever go to the fireworks on July 4th and you watch those beautiful ones, the streamers, where they all go out, and if you think about it, if you sit in the middle of a streamer as this firework goes out, and then you take a snapshot and you measure the velocity of the little ejecta as a function of distance, the ones that are going twice as fast, that started out twice as fast, now have to be twice as far away. Okay, the ones that are half as fast are half as far away. In other words, if they all start out at one time, one place, and then they explode, the fastest ones get farthest after a certain amount of time. And that's all he's measured. So what this does is it indicates that the galaxies, it's like you're at the center of an explosion, and the ones that are farthest away are also traveling the farthest, and it's a linear relationship, okay? Now, I know a lot of you in the audience, and I don't want to get too wonky about this, but a lot of you in the audience are into data and graphs, and you'll notice two things. First of all, if I took the straight line off this graph, you probably wouldn't be able to draw it on. I mean, you know, it's really a ridiculous correlation. The formal correlation coefficient is pretty low. So he had a lot of nerve to draw this. The other, you'll see why it gets worse, okay? And the formal Hubble constant he got was 500 kilometers per second per megaparsec. That means, incidentally, a parsec is 3 light years. Okay, I have to, since I've used a few of these professional slides, I'll get you. I realize none of you have any concept of what a light year is anyway, right? But at least light year is something you've heard of, and a parsec is 3 of them. So 1 million parsecs is 3 million light years. So it's a long way. Now, so he measured the distance, and he got that for every million or 3 million light years, every million parsecs you go away, the galaxy velocities increase by 500 kilometers a second. Now, let me just show you this afternoon. I've showed this plot many times, but this afternoon, just for you, I decided to do the following. I actually looked up the modern distances to all these galaxies, and let me show you a couple. This is the Small and the Large Magellanic Cloud. Okay, they're now a little different. And you see this? These are all the local group galaxies. So this Andromeda is on here. I think this is, no, this one here, I think, is the Andromeda Galaxy. It's now out here. So you see, actually, his distances were not very good. Not only were they not very good, but we now know there's a local group which consists of this stuff, And there are no other galaxies between us and, well, let me just show you where the other galaxies is. You see this little group? That turns out to be way off the chart. It's literally out there somewhere, okay? I think this group is out at 8 megaparsecs. See the 2 there, 8 megaparsecs. I plotted every other one of these. They're all off the chart. Okay. This data is complete garbage, absolute garbage. Furthermore, this is a modern Hubble constant line, which I'll show you in a minute. So he was off by an order of magnitude. So the famous Hubble law, he just got completely lucky, unless he fudged the data, which is also possible. And he's dead, so we can't ask him. But the point that I'm trying to make is the expansion of the universe, which I'll show you in a minute, has now become very robust. And I'll show you a more modern plot right now. That's a more modern plot. Notice that the point I was showing you from 0 to 2 megaparsecs, it's a kind of a little dot down there. That's what he was measuring. You really have to get out to about 100 megaparsecs before this becomes good. But now you see a beautiful linear relationship. All right, so this is a modern Hubble diagram, and I can't emphasize this enough. This is the underpinning for the whole idea that we live in an expanding universe. The expansion is linear in such a way that it blew up. If you extrapolate back from the firework, the one over the slope of this line tells you the age of the universe, and I'm going to get to that in a minute. We know that pretty accurately. All right, so that was number one. That's the underpinnings of the basic Big Bang. Now let me take this diagram and let me show you a slightly more modern approach. So this gets you out to some distance like 500 megaparsecs, okay? Now I'm going to switch on you. I'm switching to a log scale because I want to go way out. We know that once the Hubble law came about, then the quest was to find a little bit more, because the universe is expanding, okay? I said it was a linear law. You know, it all blew up. It's all coasting. But it really can't be coasting, because if you think about it, the universe has a lot of stuff in it. And that stuff likes to bind itself together through gravity. That's what gravity is all about. And so we knew for years that if we looked back far enough, we would expect that the universe at some very early stage was not expanding as fast. It was expanding faster than it was today. It must have slowed down, because gravity is just it's an attractive force. So it had to kind of impede this. So the quest came to find out just exactly what the history of this is by looking not out at 100 or 1,000 megaparsecs, but as far as 10,000 megaparsecs. I mean, way, way out there. So this was predicted, and this is the diagram I just showed you. Now this is further in the past, and this is a redshift. So now let me show you that. Okay, so those are the data, and this is what was expected. So we do see a deviation from a straight line. Okay. But the problem with this deviation is it shows that in the past, the universe was not going faster. In fact, that line shows that it was going slower in the past. And so the big surprise that nobody ordered was the universe appears to have been speeding up over the last few billion years. And there is no way that we had to explain that. So we do what scientists always do in a situation like this. We invented a fictitious substance to explain what's going on. That fictitious substance is called dark energy. What dark energy is it's the stuff that makes the universe accelerate. Now, all of you know as much about dark energy as the best experts in the world. You can explain this to your children or your siblings or your parents with complete confidence. And you should be confident that you are as expert as anybody else, because no one knows what makes this happen. Now, in showing these graphs, I've kind of elided over a very interesting and important point. So for the audience in the back of the room, you may not be aware of it, but you are not viewing this lecture in real time. In fact, I can say with a great deal of assurance that you are viewing this lecture, I'd say you're about 100 nanoseconds behind the actual real-time lecture, because it takes light about 100 nanoseconds to get from me to the back of the auditorium, okay? Good number to know is light travels a foot in a nanosecond. So those of you in the nano world, it's all kind of, but now that's perhaps not interesting because I don't say much in a nanosecond, right? What's interesting is when light travels a long distance. So remember how I said that 100 million parsecs is really 300 million light years? Okay. So that means if you're looking at something which is 300 million light years away, you're looking at that stuff when it's 300 million years in the past. Okay. Now that's actually sort of impressive, but in astronomy, that's not very long, really. I mean, it's not long enough to be very interesting. But if I go out far enough, look at this axis, and I don't want to get too much into the general relativity, but that's actually 10,000 million parsecs. That's 10 billion parsecs, which is 30 billion light years. Well, that's a long time. And I'm going to tell you in a minute that if you take the 1 over the slope of this curve and calculate it accurately, the age of the universe since the Big Bang is only about 14 billion years. In fact, it's exactly 13.7 billion years. And now we think we know that to about 2%, well, maybe 5%. And so, in fact, so what's interesting is by looking out, you can look back into the past. So in astronomy, we can do something that you can't do in any other science, and that is you can really study the history in some sense just by looking farther and farther out. And it's partly for that reason that much of the course of astronomy has been a quest to build bigger telescopes which will go deeper, which will go farther, because as we go farther and farther back, we look at the universe as it's evolved. So tonight, you're going to see it going back to the point where we don't think we can actually see back much more anymore. So now you know about the expansion, you know about the Big Bang, you know as much about dark energy as the greatest experts in the world. They won't tell you that, but that's true. The people who discovered this, by the way, Adam Riess in 1998 and Saul Permutter, and for that they're getting prestigious prizes. I'll show you one. They got the Shaw Prize in. This was just a couple of years ago. I think most everybody believes the Nobel Prize is just inevitable. And I show you this picture because look at how young these guys look. I hired him when I was the director of the Space Telescope. So I gave him his first job. Now he's going to go win a Nobel Prize. But this shows you the pace of science. This is a wonderful thing. This is very human activity. That's a good thing that we do. All right, so that's dark energy. Now, you get I told you about Hubble. Hubble was an arrogant man, and he discovered, and of course they named the whole thing after him for data which was clearly flawed, and probably, even the line he drew wasn't right, but he's now one of the most famous astronomer of that century. I'll show you another one of the characters of about the same vintage that I knew when I was a graduate student, and that's this guy right here. That's Fritz Zwichy. This was very typical of the astronomers of those days. Now, Fritz Zwichy was born in Switzerland. He wound up as a professor at Caltech for many years. He didn't get along well with his colleagues. You can see why. But Fritz, Fritz was really an iconoclast. But Fritz actually did some brilliant stuff for which nobody ever gave him credit. But he did brilliant stuff, and he was the guy who actually discovered dark matter. So now I'm going to talk to you about dark matter. Okay, it's the other underpinning. So if you look at this, this is a cluster of galaxies. And I think you can see it's a cluster just because there's so many galaxies in just a small spot. There's a lot of stuff in the background too, but you see these big galaxies? There's some other things in here I'll talk about in a minute. But the clusters of galaxies are things that you see. It's not rare, but it's also not too common. You see it out in the cosmos. And we know that if there is a cluster, something has to keep it together because these galaxies are whizzing around. And the only way they can be kept together, just like we thought with the Big Bang, was gravity. So what Fritz did is he said, okay, if the clusters are bound by gravity, then I can figure out if that gravity is due to the stuff we see. Because everything we see here is in stars. You can count the stars, not quite one by one, but it's just like weighing pennies in a jar. You get the total light from the galaxy, and then you know how much light is in one star on average, and you just divide, and you know the number of stars. So what he did is he said, okay, to find these galaxies, let's determine the mass in the stars from the light. I'll just measure the light, divide by the light from a star, get all the stars. And then he said, I can determine how much mass it would take to bind it together because I know how much gravity it would require. And so the gravitational mass that you need to bind these galaxies together is just a simple law. For those of you writing a paper, Andy will probably test you on this. And for the rest of you, you don't have to worry about the constant. But you do have to remember that there's a relationship between the gravitational energy and the kinetic energy. That is, if you have a lot of kinetic energy, you have to have more gravitational energy to keep the stuff bound, okay? So there was a simple relationship. So then he could compare the gravitational energy that he calculated from that with the gravitational energy necessary to bind it together, the kinetic energy which he measured. And what he found was that the mass that was required to bind the galaxy clusters together was about 50 times the mass of the stars. And this actually was a very robust measurement. This was quite good. He did this in the 1930s. And that number still stands today. It's been refined in many, many ways. And it was called for many years the missing mass, but what it really means is there's matter there that we don't see. That's dark matter. And now dark matter we do know a little bit more about. Not a lot more than dark energy, but we do know a little bit more about. And I'll make some remarks about that. But what's important to know is that we can measure it in this way. There are other ways we can measure it. The other most important way is what's called a gravitational lens. You can see here, see these little arcs here? It shows up in this picture. I've got a better picture in the next slide to show you, and that's this one. Isn't that beautiful? This is for the Hubble Space Telescope. You see, this galaxy here has so much mass associated with it. You see all these little arcs? Those are galaxies which are about twice as far away as this cluster. But the gravity in this cluster actually bends the light from these galaxies as it comes through, and it looks like you're looking through a fishbowl or a big distorted lens. And that's the impression you get is exactly what's there, okay? And what's interesting about that is we can calculate with the Einstein's general theory of relativity, predict exactly how much gravity it takes to do that bending of light. So we have a completely independent way of finding out if the dark matter that we calculate from these galaxy motions is the same as that. And it is. They match almost exactly. And there are several other ways that you can actually do this. And so what that means is we really know that in the universe, the amount of matter that's us, the light that we see, is small compared to the total amount of matter. And so now I'm going to summarize, this is all of modern cosmology, pretty much summarized in one slide. So now we're near the end of the first teaching moment. This is now the entire theory. So if you do the calculation, what you find is this is a pie chart which shows the composition of the stuff in the universe. About 74% of it, about 3/4 of it, is dark energy. This says 65, but this is an old slide, and I've updated it with the latest numbers. And even the uncertainties, you see how accurately we know that? We think we know that to almost 3% accuracy. I mean, it's just astonishing how well we can measure that. We have no idea what this stuff is. Absolutely not. Okay, but we know something is there to push the universe apart. Then there's the dark matter. The dark matter is another approximately 26%. The total matter is 26%. I'm sorry, these two numbers add up to 1. But the dark matter part of it is all but about 4%. So about 21% is just the dark matter. And then the rest of it is things that we are familiar with. The stars are about 0.5%. There's free hydrogen, helium, about 4%. And then the heavy elements, which make up us, give rise to the Earth, life, this lecture, 0.03%. So if you felt insignificant before you came in here, I hope you feel even more insignificant right now, because frankly, we are. We are just an afterthought in some sense in the cosmos. Most of what we've studied in astronomy is this stuff right in here, just this and a little bit of that, and some of this. But now we're beginning to see the whole picture and that picture. I'm going to make allusions to a few other things, but there are only a couple of things that are important to know. This is the age of the universe. This is our best estimate of the age of the universe with actual uncertainties. And you see, we believe we know it's 13.7 billion years. That's a giga-year, billion years. And we know that to the nearest 100 million years, more or less. Just astonishing. We know the Hubble's constant in these same units of kilometers per second per megaparsec is about 72. We know a bunch of other things. I'm going to go through some of this, but this is part of our creation story. Now, if we believe this, okay, if this is true, then it means that we can make some very strong predictions about how the universe evolved. Because if the universe did start in one spot and it blew up, we can wind the clock backwards and we can ask what the universe was like at earlier epochs, earlier times. And the next slide shows you a kind of a quick and dirty cartoon of the history of the universe. So it starts all the way there on the left with a big bang. I know that'll come up in questions, and I don't know much about it, so I'm not going to talk about it just yet. Then there is a brief period about which we know little, but then we begin to know things. Just a brief moment after the Big Bang, we know the universe was very hot, was very dense. It created the elementary particles. Those particles reacted with one another. As the universe expanded and cooled, it created hydrogen and helium nuclei. Then those hydrogen, helium, and nuclei, they're in a sea of nuclei and electrons. The electrons combined with the hydrogen nuclei to make atoms, and they emitted a whole bunch of light, a whole bunch of photons right here in this era, about 300,000 years after the Big Bang. And then that radiation decoupled from the matter. It no longer saw the matter. We can still see that today. I'm going to show that in the next part of the lecture. Then there was a long period of something like a few 100 million years after the Big Bang when we don't think that there was very much going on. And suddenly after that, what happened is matter began to clump up. And as it clumped up, it collapsed to form stars and galaxies. And it gave rise to this period of creation. I'm going to talk a little bit about this as we go on. And then over the next 3 to 4 billion years, it created planets around stars like ours. And then life on this planet arose very quickly after it could, right after Earth was created. But it took another almost 5 billion years for intelligent life to arise. We've only been around just a little tiny time. And that's kind of the history of the universe. Now, we can observe this, and it gives us a great idea of what went on later. So I'm going to show you that in a minute. And we can observe this, and that I think is neat because we have pictures of it. So now what about this period here, this microwave background? Well, as I said, about 300,000 years after the Big Bang, this was a hard prediction. The nuclei combined and gave rise to this radiation. And in 1965, this radiation was observed for the first time, and it was called the cosmic background. Now, it's very uniform radiation, and you see it everywhere in the sky, even though you're looking back, and that's a picture of it. Yeah, that's what it looks like. Pretty boring. Okay, so the thing is that it is very uniform, and it's uniform because when the universe recombined, it did it very uniformly all over. But we can do a little bit better than this because we can subtract the average of this, and we can find out just how much the variation is. So let me do a subtraction of the average. If you subtract the average, then you get this diagram. And what this means is here, this blue, and here, this is a green or red, indicates, the spectrum is meant to indicate a little shift of the radiation, a little Doppler shift. So the blue stuff is coming at us, and the red stuff is going away. Okay, red shifted means going away. And so this is called a dipole. It means if you look in one direction of the sky, it looks like the whole universe is going away from us. If you look in the opposite direction, the whole universe is coming towards us. And all that means is we can measure the mean motion of the solar system against the cosmic background. We can measure the peculiar motion of our own galaxy against the cosmic background, which we take as a reference system as the universe. Okay, and we can measure that very accurately. I think it's pretty neat. It isn't, it isn't a beautiful picture, but it is a sort of a profound picture because we're actually measuring ourselves moving in this sea of radiation. Okay, well, once we know that movement, we can subtract that out too. We can get rid of that dipole, and we can subtract it away, and then we get this. Okay, that's down. By the way, and let me just do this very quickly for the audience, this temperature scale indicates the temperature of the radiation, and so the fraction is given here. So this is about 2.7 degrees above absolute zero, and now we're going down to fluctuations of about 0.003 of a degree around that. So it's a part in 1,000. Now I'm going down to 18 parts in a million. See, it's a micro Kelvin. And what you see here is the galaxy. That's the Milky Way. So we don't see through the Milky Way very well, but we can see the microwave background above, the poles of the Milky Way. And if we subtract that, finally, we get down to the fundamental fluctuations in the cosmic background radiation, which is that. Now, that turns out to be interesting. Okay, it looks like a kind of a mess, but it turns out to be interesting. I'm going to explain why in a minute. But what you'll notice is it isn't really smooth at this scale. You have to get way down. You have to get down to 6 millionths of a degree in fluctuation to see it, and it's not smooth. But the reason this is interesting is because there are hot spots and low spots, and what that means is the universe had little places where the density was higher and the density was lower. And those places where the density of the higher were seeds of the galaxies that formed a little bit later. Now, the problem with this particular image is this image doesn't have the resolution to really see it. Most of this is because the telescope can't can't look at the structure. So recently, we put a satellite up to look at that structure. So this is the picture I showed you before. With a new satellite, we were able to measure the structure, and I'll just show you how that goes. And now that's the structure of the cosmic background. And those little things there, those are what we think are the seeds of future galaxies. That's how the galaxies will go. I'm going to go back and forth just a couple of times so you get the idea. Because if you see some of these hot spots here, you see now look at one of the red spots, and then you'll see as it fades into the next picture, it still has that red stuff, but it's got a lot more structure. So here are the seeds of galaxies, or the structures of galaxies. They're little regions of overdensity. And I'll show you how we think that the universe formed in a minute. I'll show you a movie. But I'm also going to tell you, this gets a little technical, but I think for this crowd, you're going to like this. We can tell what the structure of the universe is. We can tell a lot about the physics of the universe by measuring exactly how these fluctuations come about, just what the distance is between the fluctuations and what's called the spectrum of power at different scales. So just to make an analogy, I've got a picture here off the web of an ocean during a storm. So we live near the ocean. Some of you got out there during a storm. And what you can see in this picture, your eye picks it out right away. But technically, it's a little hard to describe. You can see there are big swells, and those big swells are kind of the big things that are a few meters apart. And any of you here who surf or just watch the waves know that the big swells is one dominant wavelength in the ocean. But in a storm, the wind kicks up a lot of small stuff too, and that's another dominant wavelength. That is, you've got at least two different structures in here. This looks like chaos, but it's not. There's really structure in here, and your eye can pick it out, but you need a formal way of measuring it. And the formal way of measuring it is to plot a spectrum, or to plot the correlation or the power in these waves at different scales, and that's just shown up here. So if I were to plot the amplitude of waves as a function of the frequency, or 1 over the wavelength, then the big waves, the 5-meter waves, they would have a big wave amplitude, and the little 1-meter waves, they would have another amplitude. Maybe there would be more peaks there. And the concept here is that you can actually take a spectrum of the power at different sizes. And I'm going to get to why that's interesting in the next slide. Now, you can do this for the universe as well. You can do this for the cosmic background. So this is a very intense teaching moment for you, okay? So what we want to do is we measure this cosmic background, all the fluctuations, and we're going to take this spectrum and we're going to look at it. And that's shown in the next slide, okay? So remember, the ocean, well, my light's done, okay? You see there's structure in here. This is a spectrum, just like this ocean spectrum I showed you, on angular scale. So that's 90 degrees, you know, that's a big chunk of this, down to 1 degree, that's a 1-degree peak, and look at the beautiful structure in there. This is not random. This is not chaos. In fact, this has beautiful structure embedded within it. And that structure is entirely driven by the physics at the time the universe was producing this radiation. Because what happens is that structure can only change as fast as sound can propagate across the universe. And so what you're looking at is you're looking at acoustic waves that were imprinted in the early universe on this radiation pattern. And the scale, the angular scale of the largest waves tells you how fast the largest things could have propagated during the time that the universe was that old. And the other things tell you are proportional to things like how much dark energy, how much dark matter, all these constants. And the data points are such that we can fit these curves accurately. And the reason I can tell you with great confidence about things like the age of the universe and the structure and looking back is because we can do something like this and analyze it with just exquisite precision. This power to get at our own creation story is just remarkable. And I realize for some of you, this is obvious, okay? For the engineers in the crowd, what I did is I took a 2-dimensional spatial Fourier power transform of that thing, and that's what you see. Got that, everybody? But really, you can see what's done. It's not that hard to see. And that power spectrum is very important. By the way, we now have it out to here, but our theories predict that if we can take this out another order of magnitude in scale, that is down to finer scales, there's tremendous amounts of information that we don't have yet that we can get out, that the theories say has to be there, talks about neutrinos, talks about all these constants. And so there's a satellite which is due to be launched, I think, within a year or two, called the Planck satellite, which is actually going to go measure this. So that just sort of a window into, when you read the press releases, you just think back to these transforms. That's what people were doing. Now, why is this important for the context of my lecture? Well, because this stuff, as I said, are the seeds of modern galaxies. And I can illustrate that. Oh, by the way, just to remind you, the main peak here is about 1 degree. So you have to have that kind of resolution to see it. So I've illustrated that with a little movie. This is a movie that was put together by my colleagues in Munich, Max Planck Institute for Extraterrestrial Physics and Astrophysics. And what this shows is it starts with the universe when the universe, this redshift parameter means the universe was about 100 million years old. And it's going to show the universe evolving from 100 million years until today. And the idea is you can see some of these fluctuations. You can see some of this stuff. That's going to evolve into the modern galaxy. So now what we're doing is the universe is evolving. We're going to later times. Now we're out at about, by now we're out to about 700 million years. Now we're past 1 billion years. Now it's slowing down. Now we're getting out to about 2 billion years. And now, by the time we get to a redshift of 1, we're out to about 8 billion years. And you see what's happening is the gravitational wells, where there's a little more matter, is sucking stuff down. And you're creating clusters of galaxies. Most of those big things are clusters of galaxies. And in between, there are these large voids. We can measure that today, by the way. So I already showed you one cluster. I haven't showed you the voids, but it's easy for us to now measure. This is the structure, the walls of the universe. Theory predicts this came about because what these are is this developed when gravity acted on the fluctuations in the detritus of the Big Bang as seen in the cosmic background. So that's now the history of the universe. That takes me up to the point where we can now begin to look back. And what we're going to do is we're going to look at some of the next stuff. Okay, so remember I talked about the history of the universe. And what we've done is we've taken you through the microwave background. We've observed the microwave background. That little movie I showed you took you from here. Well, no, sorry, it didn't. It took you from right about here to where you get galaxies and finally out here. Now, what's interesting is we can see the microwave background. But for most of the history of astronomy, we were only able to see into this part a little ways because the biggest telescopes we built, the 200-inch telescope at Mount Palomar, the 10-meter Keck telescope, wherever we looked and however far back we looked, the universe still looked pretty much like it does today. And that's because we never really got very far back. What it took to get very far back was to free ourselves from the problems of observing through the Earth's atmosphere. And that first happened when we launched the Hubble Space Telescope in 1990. Of course, it wasn't very good when we launched it, but we fixed it in 1993. Those of you remember the little mirror problem. But by 1993, we fixed it. And at that point, it became clear that Hubble actually had the capability of looking back a long way. And so this is my little icon. Hubble, in principle, can see all the way back to the time when the galaxies were first forming. And now that's what I'm going to talk to you about. Okay, now I'm going to show you as looking back, because this is kind of the neat part, a picture that you can see. So in 2004, as Andy said, I was the director of the Space Telescope Science Institute. One of the privileges of the director is 10% of the telescope time was called director's discretionary time. As a director, I asked my lawyers, they said, yes, that means it's at your discretion. So I said, okay, let's take some of that time and let's make a really deep picture. Now, this was not, I'd love to tell you this was an original thought, but it wasn't, because my predecessor, Robert Williams, who was the director just before me, had actually done that first. He said, yes, let's take a lot of time and make a deep field. And that was the original Hubble Deep Field. And the Hubble Deep Field got us back in this diagram most of the way. You could begin to see the universe change, but it didn't quite have the oomph to get back to the edge. But in 2002, when the astronauts went up and serviced the Hubble telescope, they put a brand new camera on called the Advanced Camera for Surveys. It was built just perfectly to take deep images of the universe. And with my team at the Space Telescope, most of my colleagues and I, we sat down and they calculated, they said, look, Steve, we ought to be able to actually get back to the time when the galaxies were first forming if we're willing to take a deep enough picture. Sort of up to me. I said, can we do it with 10% of the telescope time in a year? They said, no, it's going to take more than that. So I said, fine, I'll take 10% from one year and I'll take a little bit more from the other year, and we'll start in the mid-year and we won't tell anybody about it, which is what the factor did. And that's true. But although we did run a community process, we were very careful. And I actually had many committees and asked people. And people eventually said, look, this is a pretty good thing. It's sort of, if you bought a Ferrari, don't you think once you'd want to see what the top speed is? I mean, that's kind of what it's like. So we had the Hubble Space Telescope. Don't you really want to see how far back you can see? And it was like that. So we started out on what's called the Hubble Ultra Deep Field. And in September of 2003, we took the telescope and we pointed it at one spot in the sky, which is the blankest spot we could find. We tried to, avoided stars, avoided known galaxies. It was just the darkest spot we could find. We started exposing the telescope and we observed for 40 days and 40 nights, and then we rested. Told you it's going to be a revival meeting in just a minute. And the thing about, we wanted a square picture, and if the thing is that you don't think about this much, but when the Earth's going around the sun, so you can't observe for very long before the whole thing starts to turn. So we just observed for really 40 days and 40 nights while the telescope's going around. So probably every day we had 18 days and nights, but that's a little net. And then we did pause. And then again in December, we started again and we observed for another 40 days and 40 nights, because by that time, the Earth had gone around far enough that we could rotate halfway. So we get a square picture this way. And then January 16th, 2004, the same day that Sean O'Keefe stood up and said there would be no more servicing missions to the Hubble Space Telescope, we took the final exposure. And we had a 1 millionth second exposure with the most powerful telescope ever invented of the darkest spot of the universe. And we call that the Hubble Ultra Deep Field. So let me show you the Hubble Ultra Deep Field and show you a little bit about what it means. So this is a picture of the Hubble Ultra Deep Field. Now, so on the top, I've shown you the universe is now 13.7 billion years old. I think this is failing. On the right-hand side, I've cut out a bunch of galaxies, and on the right of those are numbers. The numbers are the time after the Big Bang in billions of years that the light was emitted. And so on the top, you can see that galaxy is pretty ordinary, and that's because the universe was already almost 9 billion years old, which was pretty old at that point. I mean, plenty of time to form a spiral galaxy. But when you went back to 3.3 billion years after the Big Bang, it's more typical of that train wreck type stuff I showed you. It's about the size of the galaxies today. So, I mean, it's still big like the Milky Way, but it hasn't had time to really fully assemble and settle down into nice waves or to nice spiral galaxies. As you go back farther, you see two trends occurring. One is this regularity, it gets even less regular, but the stuff gets very small. And then when you get to below a billion years and 800 million years, it's that little red thing down on the right, you just get little clumps of matter. And so what you're looking at are the first seeds of real galaxies early on in the Milky Way, in the universe, the first seeds of real galaxies, and those will later grow to become the spiral and elliptical galaxies we see today. I'll show you two kinds of pictures to get an idea of the statistics. One of my colleagues, Deborah Elmgreen, and her collaborators went through and they just tried to identify weird shapes. This is something that both astronomers and butterfly collectors are really, really big on, is to just categorize shapes. But it's pretty neat because this is the first time we've had a picture this deep and we've been able to look back. And you can see she calls chain galaxies, clump cluster galaxies, double galaxies, tadpole, etc. Down in the bottom are normal spiral and elliptical galaxies. So this is what we see today. And that stuff is what you saw mostly in the early universe. Now, it's difficult to take these slices unless you know exactly how far back you're going. And so this is one more little teaching moment. I'll tell you how we work that out. Let me come back to, because the universe is expanding and because there's a correlation between the distance and the velocity, at some point, because we can measure velocity very accurately with spectra, but we don't know the distance, at some point we just measure the velocity and that tells us the distance. And so we can measure the velocity because as things are going away from us, the light is shifted more and more into the red. And here is the way it works for a typical galaxy. This is a series of spectra. It's probably a little washed out. This is the typical spectrum of a galaxy. This is the edge where hydrogen absorbs everything. This is in the ultraviolet. And then these are the normal filters we use to observe: the blue, the visual, what's called the infrared, and a deeper infrared filter. These are the wavelengths and angstroms. And you see, this is the spectrum of a galaxy that's nearby. If you looked at a spectrum of the galaxy where the universe is expanded, what's way out, so the redshift of this is 1. That is, it's almost double the wavelength. This 912 angstroms goes out to 2,000. You see, this whole thing shifts out to redder wavelengths. And as you take that out to farther and farther reaches, what happens is this edge where hydrogen absorbs everything, pretty soon it kills all of the light in the short wavelength filter and leaves light out here. And if you take that out to a very high redshift, it'll kill light in these 2 filters. So what we've learned to do is to identify galaxies, but it's what's called dropouts. That is, if a galaxy is this far along in redshift, it drops out of this blue filter, and you only see it in these filters. And if you look on the right, you see I've got one of these galaxies. This is the Z, the I, the V filter, and whoops, there it goes. It's dropped out of the V filter. So just by looking at this image, the color of this tells you that this is out where the redshift moves the light out by a factor of 4. And for a redshift of 4, that means the universe was about 3 billion years old. We can calculate that very accurately. So this is what's called a B dropout. And so by using this technique, we can then just go through all the galaxies and we can look at where they drop out. And we can put slices of the universe. And if we do that, then this is the most distant slice. So this is what we call I dropouts. That is, you only see it in one filter. These are the distant red things. And so all of these are galaxies, or the proto-galaxies, I guess you'd call them, the clumps that will become galaxies. And the light was emitted when the universe was between about 700 million and 1 billion years old. Now remember, today it's 13.7 billion years old. So that's a little bit like if I'm, in my 50s, you could, by looking far enough back, I mean, if you were far enough, if this lecture hall was big enough, you could see me when I was only 3 years old. Now that might not be interesting, okay, and that's a long way away. But that's sort of the idea. What you're really doing is you're looking at the universe when it was only about 5 to 7% of its current age. And I'm now going to overplot what the Milky Way would look like at that distance, apart from the color. So that's the Milky Way at high redshift. Now the Milky Way would, of course, be very red, so it doesn't reproduce the color. But look, this is the actual size that the Milky Way would be compared to the size of those objects. So you can see you're looking at a whole bunch of stuff that doesn't look anything like our current galaxy. So this is the universe when it was very young. And we ought to be able to go a little bit farther back than that, but not much, because we're very close to the edge. Now, what happened after that? Well, what are we looking at? Well, let me just give you an idea of what the universe did. So this is a movie I'm going to show you. This is my second movie of 2 colliding galaxies. And this is kind of neat. This is theoretical calculation because we can't watch this happen. It takes a long time. See, it's measured in hundreds of millions of years. But you see these 2 galaxies coming together. The idea is, in the early universe, you had a lot of these proto-galaxies. And in the clump clusters and things, they began to get together and they collided. But when they collided, they'd eventually bind. They'd leave out streamers. But you see, even these 2 galaxies don't get away from one another. They're going to come back together again. And it's a lot of that gas streamer, which is really a set of stars, is coming back together. And it'll kind of merge, and it'll make a lot of stuff. And even though this is a theoretical calculation, I'm going to show you on the next slide, that this actually reproduces things that we can see today. And so this is what the buildup is going on. This is our creation story of how we got to the galaxies we have. And we can see that. We can see that today if you just take an example. So here, now take a look at that with the nucleus and the streams coming out. And then here, this is a picture from the Hubble Space Telescope of 2 galaxies which are pretty close to us. I mean, but in this business, and you can see these are 2. They have 2 nuclei. You can't see them very well, but these are 2 galaxies that have collided nearby and created these streams and so forth. And so that's it. That's how the galaxies built up. And we can, by looking at these pictures, by looking very far back, we can now piece together a time history of how the galaxies were formed and how the universe evolved, really starting even before the microwave background, but that's the topic of a completely different lecture. And then through the microwave background, all the way up to where the galaxies are forming, and all the way up to where we are today. So now that's the main part, but let me wrap up here by talking a little bit about the future. Because I've kind of given you an idea of the power that we've got with these modern telescopes and techniques. of teasing out just the most incredibly precise details of what the universe was doing at early times, and it all fits together. Our creation story is very evidence-based. This is a creation story essentially of Western civilization, and it's based on observations and data, and it's remarkable. In the future, we can test this in lots of ways, and I've just showed you a few things. Some of the people in this room are probably even associated with these things. There is, for example, the 30-meter telescope. That's not, it's a project. Hasn't been built. This would be the successor to the Keck telescope. California, still, for many years, and I think still, would be considered the center of astronomy in the world. The Europeans are trying to take it away from us, but we're still pretty good. And this was true at the time of Hubble because of the telescopes in Pasadena. It was true at the time later on in World War II. The Palomar 200 telescope was built. Then the Keck telescope was built in the 1990s. That's a 50-50 collaboration between the University of California and Caltech. The 30-meter telescope is the plans for the next big one. That's a collaboration between the University of California and Caltech again. And I'll talk a little bit about this. But what's interesting is there are a bunch of things that we can do. And let me just talk about what that looks like. There we go. Okay, this is the 30-meter telescope. One of the problems that we've got in looking back at the early universe is with Hubble, we can take pictures of these galaxies, and I've showed you the shapes. But we can't collect enough light to actually take spectra. And it's spectra that tells us about the dynamics and will tell us about how all this stuff builds up and how it comes together. Without spectra, we really don't have enough information to put the story together. The problem with spectra is Hubble is collecting all the light it can, and it's just limited by its ability to capture light as it comes down, to capture photons. The only way around this is to build a big collecting area. There's no other way to do it. You just have to collect more light. And so the project plan for this, a 30-meter telescope, and there are a number of these things on the drawing board now, this is the California telescope, is to build a big telescope that would allow us to actually go through a field like this, take spectra of the different galaxies, and understand the dynamics, actually figure out if they were actually assembling or not. Here's another notion, and this doesn't require big telescopes. This requires big data rates, and that's of interest, especially in Silicon Valley. So let me digress a little. This is a theoretical picture of how structure is developing. Now, remember I showed you the movie, and you just saw the sort of face-on view of stuff as it clumped up, and this shows you a sort of a 3D view. Well, the exact way in which this clumps up depends very critically on the properties of the dark matter and the dark energy. And because we know nothing really about the dark energy, except that it exists, and we know a little bit more about the dark matter, that is, we have some ideas about what it might be, and we're doing experiments to test for that, it's very important to figure out what the properties are, and one of those is just by measuring stuff in the universe. Now, remember, what I'm showing you is collections of billions of galaxies in different distributions. So how would we work this out? Well, one way we could measure this is simply by you don't even need a big telescope, just measuring several million galaxies, measuring exactly their positions, exactly their velocities, going out deep enough that you can see it from an early time in the universe to now, and then you can just plot these, and you can take different slices of the universe, and you can watch how the structure develops. That's one of the next big experiments that people are very excited about. Here's another one, and this will be my last part of this to teach you before I finish off and take questions. Remember, this is the cosmic background, and the key to understanding how the universe was constructed was to look at the structure of that cosmic background. Okay, we did what's called a spectrum of the spatial scale differences. You can apply that same technique to galaxies. And so this is what the remnant structure should be on the galaxy distribution. This is a prediction now. This is not a measurement. This is a prediction. And your eye can immediately see, just by looking at this, your eye can immediately see clear structural scales in here as a result of those. This is the result of gravity. And so what we predict is that you can measure waves in this, both the transverse waves in the sky dimension and the longitudinal waves along the dimension, and we could study this as a function of distance or as a function of the age of the universe, just looking back. So what does this require? Well, it just requires us to take a telescope with an enormous number of detectors. So right now, in my laptop, the screen has I guess 1,400 by 1,000 pixels, which is considered big. We want telescopes where the entire focal plane of the telescope is peppered with pixels. Typically, we want more than 1 billion pixels in a camera for a telescope. That's possible. And if you put it up into space with 1 billion pixels and data rates where you're getting petabytes of data every few weeks and have to analyze them, we can get the entire structure of the universe. And it doesn't even require a telescope as big as Hubble. You can do it with a much smaller telescope, just a lot of pixels. So Moore's law has worked to help us because it provides us with a way of making this kind of measurement. And this is kind of a prediction of sort of the same kind of spectra, where you get these bumps in the spectra, and the bumps tell you, this is a sort of a theoretical plot at different periods of the universe, at high redshift or early times and then more recent times. If we have the patience to make these measurements, we can actually see how the structure develops and understand something about the dark matter and the dark energy. Well, how does this come about? How does our creation story result? For most of human history, the best we could do to look at the sky was simply to go out and look at it. There was that. In 1608, Galileo heard of a device called a telescope that was invented, or at least being sold on the streets of Holland. He was very smart. He could figure out from the description what it must be, and he went and he built his own couple of telescopes. These are pictures of the early telescopes. They're very small. They were only a few centimeters, the lenses, a few centimeters in diameter, but pretty long. And with those telescopes, he actually increased the ability to observe the universe, the power over the human eye, by almost a factor of 100. Just an enormous leap at the time. And with those telescopes, he was able to immediately verify a number of scientific predictions. So I think most of you know that he saw mountains on the moon. He could see the moon, and he realized the moon was like the Earth. That was a big discovery, and it was easy. He just looked at it. Wow, it didn't take a lot of work. Right? It took a little more work to understand that those things going around Jupiter were actually moons. But he realized that unlike the cosmology of the time, the Earth was not the only center of motion in the universe. It was clear that Jupiter was a separate center of motion. At least it was the smoking gun that maybe Copernicus was right. What really proved Copernicus is that the phases, see these phases? Those are the phases of Venus. Venus has phases just like the moon. Our eyes aren't quite good enough to see that, but even with a good pair of binoculars, you can go out, if you're just patient, when Venus is in the evening sky, you can see a crescent Venus. And then when it gets around to the other side, it's smaller, not as bright, but it's round, right? Just like the moon. But if you think about it, the phases of Venus differ depending on whether it's going around the sun or going around the Earth. And Kepler knew that. And Kepler had actually published this as a test of whether Copernicus was right. And Galileo verified it. It took about a year to 1609 because he had to wait for Venus to go all the way around a couple of times, but he was actually able to verify it. And when he verified it, he immediately wrote to Kepler. But because of the church and all that, this was not, this was kind of against the going trend. He wrote it in code. He wrote a riddle to Kepler. And Kepler was too stupid to be able to decode it. So eventually he had to go public and say, well, this is what it is. Of course, you know what happened to him after that. That wasn't so good. But that was a discovery that just resulted from the fact that he could observe something. Okay, it wasn't as if he said, yes, he could observe something. And throughout the history of astronomy, we've built bigger telescopes, and we've improved those telescopes with different kinds of things, eyepieces and other things. Eventually, the biggest improvements came in the last century, not from larger telescopes, but from techniques such as photography and eventually electronics. And you see the rate of progress was actually rather slow since the time of Galileo, except for one thing. And that's when we launched the Hubble Space Telescope. And that is the power we got from the Hubble Space Telescope. More than 2 orders of magnitude greater than anything we had before. That's why I can give you a lecture like this tonight. And in fact, you'll notice that this Hubble Space Telescope plot is not just a square. It's a sloping curve. And that means that every time the astronauts go up and service the telescope, we put new instruments on. And those instruments are more powerful. They take advantage of Moore's law. They take advantage of the advances in semiconductors. We get a whole new observatory. When Hubble is serviced in May, It's going to increase the power of Hubble's observations in the infrared by a factor of 20. It's going to increase its ability to observe spectroscopy in the ultraviolet by a factor of between 10 and 50, depending on the experiments. We're going to have a whole new observatory. So if you liked what you had until date, it's going to get even better. And what's interesting is because we've realized that all these kind of great discoveries, the ultra deep field, but lots of other stuff, the iconic figures of, star formation regions, it comes about partly because we're clever, but mostly it comes about because that stuff is out there. And as soon as we have the ability to observe it, we do. We discover it. It's all done almost by accident. Our ability to understand the universe increases in direct proportion with our ability to observe it. And so, taking a cue from this for discoveries, the next telescope that's planned, and this is now scheduled to be launched in about 2013, this to succeed Hubble, is called the James Webb Space Telescope. And this is what we predict the power of the James Webb Space Telescope will be. So those of you, especially in the Valley, who understand the accelerating pace of innovation, look at what's happening to astronomy. And look at this. This is over 5 centuries. And it's this last century, in fact, frankly, it's the last couple of decades that have produced the biggest, bang for the buck. A lot of bucks, but a lot of bang too. So this is our creation story. And we are very confident that we know a great deal about it. We know the age of the universe. We know something about the composition. We know a lot about the history. I can even show you pictures, as I have, that if you look back in time, the universe doesn't look anything like it does today. It looked different back then. It was a different universe. The universe has evolved. This is a creation story that everybody can understand. And it's uniquely our creation story because we've created it. Frankly, I'm sure people in the audience have made that possible in a way I never could, just through the use of technology, because there's an intimate relationship between technology and our ability to do something and what we get. And so I'll wrap up with this. I'll thank you for your attention. I'd be happy with questions. Thank you very much.
Recently, I heard that there's a dim radio wave background that's been discovered. And I was wondering if you could reflect on that and what the implications would be.
Wow, you caught me by surprise. The background I showed you, the microwave background, is that's actually what we would call radio. I mean, that's a few centimeters, so that's radio. So I don't know. I don't think you're being confused by that, but that just sort of dominates in that part of the spectrum. That dominates the background. Now, are there faint other things on top of that? Yeah, there are various kinds of things, and there's an X-ray background. It's at different wavelengths, but that comes from galaxies, the sum of galaxies, X-ray galaxies. And I don't know about the radio background. I'm not quite sure what you're referring to, but it could be that it's out there.
So the very earliest little red dot galaxies that you showed us, what can be said about the stars in those galaxies, if they were, and what were their lifetimes, and did they have supernovae, did they form heavies, and could their life have evolved on those theoretically on those very earliest galaxies?
Those are superb questions, but they're pretty expert questions. I can tell you know what you're talking about. We know, well, so let me just answer you sort of professional to professional. I mean, we know we're probably looking at predominantly blue stars because this is, even though it's in the infrared, this is ultraviolet light because of the redshift. Almost certainly there are a whole bunch of other red stars there that we haven't seen because we haven't looked at long enough wavelengths. I'm sure there are heavy stars because they're massive and blue. I'm sure there are a lot of heavy elements and supernovae. It's James Webb Space Telescope, which is designed to answer that question because it goes into the infrared and it'll be able to kind of look at the distribution of different kinds of stars in a way we can't just yet.
Yeah, I liked your fireworks analogy, and I was wondering if, since you can measure the direction of the movement of the galaxies, can you generalize where the Big Bang started in a certain part of the universe?
No, I didn't take the time to explain it, but this is one of the interesting little conundrums. I'll give you it's like the car talk puzzler. I'll give you a thing that you can do at home. So it turns out you don't need to have any center. On that firework ball, the expanding spherical ball, if you were on any one of those fragments, you would still measure an exact Hubble's law for all the other fragments in there. It's just a geometry question. So if you just assume that's true, if you take 3 points and you say from one point, you got a Hubble's law here and a Hubble's law here, and then you measure the distance between those 2 points and the velocity, just by projection, you'll see it's the same Hubble's law. So from Hubble's law, you can't identify any center, and we don't think there is a center. We believe that at least within what we call our event horizon, which is out toward the most distant things we can see, it's kind of the age of the universe times the speed of light, everything is more or less democratic. We don't see any differences. So we can't identify a center, but we can identify movement with respect to this whole sea, because our galaxy, just like others, has a peculiar velocity as well as a systemic velocity.
I'm interested in some of the details on how you made the ultra deep field image. You mentioned it was a 1 million second exposure and there were four filters. Was it a continuous exposure for the long duration of each of those filters, or was it broken up into a number of small ones?
Oh, no, it was broken up into many, many frames, and for some fairly obvious reasons. So one reason is that when you're out there in space, there are a lot of cosmic rays. I mean, there are charged particles, protons, neutrons, muons, stuff. And when a cosmic ray goes through your detector, we use CCD detectors. They're silicon detectors. They're very much like what you use in your camcorder or your digital camera, except they're more expensive by 3 or 4 orders of magnitude. But what will happen is you actually, some of your cameras, you'll see this too. If you're at a high mountaintop, occasionally you get a cosmic ray, just gives a little bit of charge in there, and it creates a blemish. And that's very, very common in space. So what you have to do is you take pictures in shorter exposures. Typically, we would take half-hour exposures. And then between every exposure, we dither. We move it by, 1 pixel or maybe 5 pixels, and we do these little patterns of dithers. And we basically do that for 1 million seconds. Then we change filters too. So you want to mix up the filters. It's the planning for it is extremely elaborate, because you want to beat down all the systematic problems of this. But by doing these dithers, what you can do is then you can compare any 2 exposures, and when a cosmic ray is in one, it shows up as a big spike, and you can just toss out those pixels and then average all the others. So we did that. It took quite a while to reduce the data, to remove all those artifacts. And so when we took the last image, we didn't really have a picture. It took another several weeks to kind of undo the dithering and do all that. And that was an interesting time.
So I'd assume that even though you have these exquisitely sensitive detectors, the light that you're receiving from the distant galaxies is, so feeble that you'd have some sort of a signal-noise ratio issue
per exposure.
Per exposure.
Yeah.
Do you expect that if you could take longer exposures, you could see perhaps even more detail, more distance? Yes. And do you have any plans to do so?
Well, I'm no longer the director, so what am I going to do? My successor may decide, but he's going to have to invest a lot of time to make much of a difference. It is the noise in the formal language. The noise statistics were perfectly normal and Gaussian all the way down throughout 1 million seconds. So we believe we have systematics under control. We could do another 4 million seconds and still get down, but it's a lot of telescope time for what you get back. But these detectors are exquisite. So the photon rates we're counting, I mean, this is kind of impressive. We can see objects in there where you get about a photon per minute. 1 photon per minute. Okay, and we get that after a long time. So it's pretty good. Hubble could easily detect the light from a lighted cigarette at the distance of the moon.
I'm curious about the fact we're getting better and better instruments, and it's going to be kind of exciting to watch it over the next decade. But if we can only see 13.7 billion years maximum, because that's the speed of light, what will we ever learn about what's beyond?
Well, that's a great question. That's kind of a deep question, but let me give it I don't want to be too long-winded, but let me give you a flavor of the answer. Wasn't it remarkable how much information you could get out of that picture of the cosmic background, which looked like a bunch of speckled noise? And we got that information out by taking the spatial power spectrum and looking at those wiggles. And if you can measure that accurately enough, you can tell exquisite detail about the acoustics and all that stuff at that age of the universe. There are similar predictions about the radiation patterns if you measure it another way. So one thing that we haven't measured yet is the polarization of the cosmic background. And that polarization depends on the gravity waves. And if we can measure the effect of the gravity waves imprinted on the cosmic background, we can extrapolate back to well before, a millisecond before the Big Bang. We can go all the way back. The other thing is many of the things that we know about in the first 3 minutes. By the way, if you like this early stuff, there's a beautiful book. It was written about 30 years ago, I think, by Steven Weinberg called The First 3 Minutes. It's just a beautiful book. And the physics has not changed, where he shows why we know what happened in the first 3 minutes. Because we can predict from the universe expansion rate and the fact that there were just protons and neutrons, we can calculate the reaction rates, what the fundamental element distribution would be after the Big Bang, and then measure it. And it's mostly light stuff, deuterium, lithium, hydrogen, helium-3. But when we measure it, we can actually show we know exactly what the conditions were like. So there are many different imprints from that early era on things we can measure today. It's a whole lecture in itself, but it's just phenomenal how much we know. I have friends who are very confident they know what happened, 10 to the minus, 14 seconds after the Big Bang. I think they're kind of nuts, but they're reputable, more reputable than I am. So, yes.
My math is a little bit lacking here, but that tiny little red dot, far distant galaxy, which emitted that light about 13 billion years ago, has been traveling that long to get to us.
Yeah.
At the time it was emitted, how far away were we from it? And at what rate are we receding?
Right. Well, we were much closer. In fact, so that's one of the interesting conundrums. Because the universe is expanding, the thing that we're seeing that's 13 billion years ago is actually now about 39 billion light years away. That is, it's about 3 times as far away from us as the distance. It's not linear because it's still going after it emitted its light. We're all streaming away. And so how close were we at the time? I couldn't, I think on the stage here, I just can't get that calculation right, but we were a lot closer than we are today. How's that? We're pretty damn close.
And so then are we actually receding from it at something pushing the speed of light?
I'm not sure I understood your question. Maybe.
Well, supposing we were 2 billion light years away from it at the time.
Yeah.
And it's taken 13 billion to cover that 2 billion distance.
Right.
Somebody's moving away from somebody else really fast.
Right. Yeah, there are things we believe. Depending on your cosmological beliefs beyond the event horizon, we have no evidence that the universe actually stops beyond where we can see it. So we would imagine that there's a piece of the universe that's farther out. But now we're getting a little bit into pseudoscience because we can't make measurements, so we can't check that out. This is a great question. All these are great questions, but they'll take a whole lecture, and we have to eat. So,
one topic you didn't touch on is inflation, after the Big Bang, and I'm wondering, what do we know about inflation from the measurements we've currently been able to make, and what can we hope to learn about it from these future measurements you've projected?
So, just for the audience, there is a conundrum that I haven't quite. I elided over, but some of you might have picked up. So if I look in this direction, 13 billion years, and I see something, 13 billion years back, right? Now I look in that direction, 13 billion years back, and I see something. It turns out we have looked far enough in each direction that we know they look the same. The universe pretty much looks the same wherever you look. Well, that's a problem because the stuff on that side and the stuff on that side could never have been in communication with one another during the entire history of the universe if it was just the expansion I showed you. So inflation was invented by a scientist named Alan Guth at MIT, I guess about 20 years ago, to take account of this problem. What he said was in the very early universe, and by very early, I mean 10 to the minus 30 seconds after the Big Bang, so really early, there was a period in which the universe expanded, underwent a phase transition faster than the speed of light. So this sounds magic, and it did to me too, but then it has consequences. So it turns out that inflation has an imprint on the pattern of the spectrum of the cosmic background that I showed you. Not the first big wiggle, which is just acoustic, but all those higher wiggles, inflation has predictions on that. Inflation especially controls the gravity waves, which then affect the polarization. By the polarization, I mean that there's a little bit more light. It's kind of going in this direction than going in the other direction. Or there's actually what's called tensor polarization, which means it's a little more complicated. And they've started to make some first measurements of the cosmic background polarization with balloons in Antarctica and telescopes down there. And so far, they've been able to show that it's completely consistent with inflation. In fact, consistent in a way that it's not just an accident. I mean, a lot of other stuff is ruled out. So there have been a number of new observations that really do probe the predictions of inflation. Another prediction of inflation is, remember I showed you those seeds of stuff that become gravity. Now, there is a spectrum of seeds. That is, it's not just, there are more big, well, roughly speaking, there are fewer big ones than little ones, okay? There are a lot of little ones and fewer big ones. And the distribution is called a power law distribution. That is, if you plotted the number as a function of size on a plot where you have logarithms on both axes, it would be a straight line of power law. Now, inflation predicts that power law should be just a little bit less than 1. While other theories say it's just exactly 1, but it says it should be just a little bit less than 1. The best results in the cosmic background now of that distribution is that it's something like 0.95 plus or minus 0.02. So it really is coming in just like inflation. It's not 1. It's really, and so that's not a resounding, it's not like a many statistical deviation result. But it's pretty good. And so inflation right now is looking very good. There are a bunch of things that people are making measurements of. And in the future, there will be more, especially the polarization of cosmic background, a much better measurement of this spectrum of fluctuations. And even the stuff I showed you about measuring the positions of the galaxies. And here, it's good to have some jargon because you can impress people at cocktail parties. So that feature of measuring the spatial distribution of galaxies, that's called baryon acoustic oscillations. Okay, baryon acoustic oscillations. Because the stuff is baryons, protons, neutrons, that's baryons, okay? And so the stuff we're made out of is baryons. And it's acoustic because it was a result of these sound waves in the early universe, and they're oscillating, right? So that's what you measure.
And the images you had where it was like just a small red seed galaxy, how far away or how far back in time is that? And is that the limit that Hubble can see, or how far back Hubble see? And can the next telescope look back further?
Yeah, well, there are a lot of yeses in there. So first of all, I said we could look back to less than 1 billion years after the Big Bang. So the Big Bang was 13.7 billion years ago. So we're looking back 12.7 billion years or a little farther, almost to 13 billion years. So that's the age we're looking back to. Hubble could measure farther back if it had a little bit more power at longer wavelengths, because we ran out of wavelength. The redshifts things to the longest camera. There's a new camera that's going to be installed on the next servicing mission, an infrared camera. It'll be 20 times more powerful than anything we've had. That, with Hubble, should be able to measure go back even farther to within, 500 million years or 400 million years of the Big Bang. Then the James Webb Space Telescope is actually dedicated entirely to infrared wavelengths. It'll go out to 20 times the wavelength of visible light. Hubble just goes out to a few times the wavelength of visible light. And that's actually built to be able to go beyond what we think is there. That is, we want a clean experiment. We don't want to have anything left over. It should have the power to see things where we don't think there's anything. So it'll be able to say, yes, there was an edge. We don't see anything beyond that. And that's 5 years away, probably.
I had 2 questions, and they were both partially answered already, but just to cover them. On your first graph of the Hubble time constant, not the very first one, but the one with the log scale that took us way back.
Yeah.
Some of those galaxies were further away than 13.7 billion years. And I think 3 questions ago, you mentioned about the age of the galaxies that it could see were actually further away now. So that axis maybe is further away now?
Yeah, it's a bit of a cheat in the sense that for the audience here, distance is something you're used to. And so I've cast everything in distance. Astronomers at this point don't use distance anymore. It's not very meaningful to us. We measure things in terms of the redshift. We actually just use the redshift as the proxy for what we want. So normally what you would do is this would be some other kind of a distance. And there are various ways you can measure distance in general relativity. There's a luminosity distance, there's an angular distribution distance, and so this is one of those general relativistic distances, which I've been a little bit fast and loose with for you because, you know, I've already tried to bend your mind too much, and there's a limit. So be careful about taking that literally. I mean, that's not quite exactly 10 billion parsecs in the distances that you're used to, but it serves well enough for the illustration here.
Yeah, it would have been, I guess that would have been 30 million light years.
Something like that. Yeah, I mean, that's something like 30 million light years. Right?
And then the other half of that, my question was on those tiny red proto-galaxies. If you were actually at that galaxy, you wouldn't have seen the light red shifted when it was emitted.
Right, it would have been blue.
Exactly, it would have been the blue light. So to compare those with what they look like versus today's galaxies, we should only look at the
You are
filter.
exactly right. And that was one of the biggest problems we had when we first made these measurements. Everybody picked up on that. And they said, look, if you looked at our galaxy in the ultraviolet, it looks different than it does in the visible. And I compared, you're exactly right. I showed you a visible light of the Milky Way, but what you're looking at is an ultraviolet picture of the early galaxy. But we did check. I mean, so what we did is we couldn't do the whole Hubble ultra deep field in the infrared because the infrared camera is small and kind of puny. But we were able to check some galaxies back there with infrared images that actually looked at not quite visible light, but blue light, let's say, 4,000 angstroms. And every time we've been able to check, the shape that you see there is pretty much duplicated in the infrared. So we think that that's really the shape you're looking at, even though you're exactly right. It doesn't necessarily have to be, because the ultraviolet light could look different. And that's one of the reasons that the James Webb Space Telescope is an important thing to do, because we'll be looking at long enough wavelengths that we'll be looking at rest frame visible light at the edge of the universe. But of course, it's shifted out into the infrared. And that's one of the reasons we build these things. So very, very, very good, very perceptive. Andy, is he in your class? You should get this guy. Recruit this guy.
Thank you, Dr. Beckwith. My understanding of Stephen Hawking's thinking about the source of the Big Bang is the most developed element, uranium, emitted than the most elemental ones of helium and hydrogen. Is it possible that there could be another Big Bang?
I will try to give you a professional answer, but I'll say right now we're pushing up the boundaries of my knowledge. Okay, this is sort of an area of research that I don't do personally, and so I'm not quite as confident about telling you what we think. But the thing is that with inflation, it turns out when inflation happens, it happens because there's a kind of almost like the phase transition is triggered by something, and the universe suddenly expands, and the field that makes it expand then decays away. Now, it turns out if that happens, then extrapolating, like now we're in another period of acceleration, and that field may decay away. When the field decays away, you can wind up getting portions of the universe that shrink down or become disconnected causally from other portions in the universe. In fact, you get so many of them, it's very embarrassing, that the inflationary theorists now, and I heard Alan Guth give a talk about this just 3 weeks ago in Washington, think that there may be many universes, multiverses, okay, where other Big Bangs are going on as we speak. Now, I don't know quite what that means, because if it's causally disconnected and we can't do experiments, it's kind of like angels on the head of a pin. But this kind of thinking is very legitimate among very smart people. And so I think you can't discount that. They'll follow this, and just like the original inflation, maybe they'll make predictions that eventually we'll measure, and that will be good. So yes, that's a sort of an interesting line of thought, which at the moment I would say is just ideas, but may become more important later on.
I have heard theories that say that the universe might have come from nothing and will eventually collapse into nothing, and that everything we believe in is just relative. Have you heard about this? And if so, is it
every day
or have?
Yes. Well, so the nothing part at the beginning is pretty good, and we don't know where it came from. Theories are nothing. Incidentally, in physics used to be good about nothing. Now it's not, because physics realized that nothing is a fluctuating sea of somethings. And so the idea is that the universe might have arisen from nothing by a fluctuation and then just expanded, and then that's what we got. Now, it used to be we thought it might collapse back. So when you say the collapse back part, that part was all about the gravity in the universe eventually slowing it down and making it collapse back. And we thought that's what was going to happen. But when we made these measurements, the big surprise was that it was actually slower in the past than now. So it's not only not collapsing back, it's actually speeding up. So unless we have some reason to know the speeding up will stop, right now, the best theory is it will never recollapse. We don't have any thought that it will go back to nothing. It will just keep going. Now, it could just expand so fast and accelerate that in the end it becomes nothing again, just because it all gets so spread out. But that's, I think, beyond the, well, it's certainly beyond my competence to think about right now. So I can't give you a good answer. But what you've heard is kind of right, and it's very interesting to think about.
So as far as right now, we still believe that the universe will keep expanding forever?
Yes, and it's very uncomfortable. So I'm pretty sure we'll figure out some way why that can't be true. I mean, we don't really. I don't like it. I mean, it just doesn't smell right. So I mean, it'll decay away. Something will happen. I know some clever person, Andy Guth or Stephen Hawking, will figure this out. But but right now, all the evidence is it just keeps expanding forever, and there is. Certainly, some of the constants I showed you couldn't tell, these omegas, indicate that it cannot collapse again. That we believe very strongly right now, it cannot collapse.
Thank you. I'm intrigued by the pie chart that you showed earlier on, and how much of it is dark energy and dark matter, etc. When we're looking back through the universe, our time exactly. That's it. We've already alluded to the fact that we have a light cone of it in our past, and therefore there's certain information you can't see that you won't see until sometime in the future, till that light gets to you.
That's right. So
when you do these calculations, do you do them for one slice and say, but you don't know what's outside of it?
I think for the calculations that predict a measurement that we can make. With the exception of inflation, everything is within a light cone. Now, inflation changes things. So you can in principle go back before inflation, and that changes all the light cones. But I think things were so scrambled then that the only real prediction you get out, well, maybe the only is too strong, but the one prediction is just this spectrum of fluctuations. That you can get out from before inflation, and that's probably outside our light cone. Other things that are outside our light cone are literally beyond our event horizon, right? So the question of what happens when you go beyond 13.7 billion years, well, that's beyond our event horizon. We don't know. And there, I think that if there are people who will make theories about the universe, and if there are measurements, like if they say, let's say the universe has an edge, like at 15 billion light years, there was nothing there. Well, it turns out that would have ramifications. You'd see the imprint of that here. It's not as if you can just get rid of stuff altogether and not see some imprint. So there are ways that you can theorize about what's outside the light cone, and it might have an imprint within our light cone just because you need a certain uniformity, and there was communication back then. But by and large, the things I've showed you tonight are all within our light cone. And for that reason, maybe a little pedestrian. But Andy will invite, Alan Guth. And
you alluded to dark energy being discovered by the supernova surveys and stuff. I'm curious if there was any data on supernova events in the Hubble Deep Field data that you got.
Oh, yeah, that's in the actual Hubble Deep Field, there turned out there was a very important supernova that we only discovered 10 years after the picture was taken, because someone thought to look and went back and looked at the frames. Because you take these frames for months, and so you can actually see the supernova, and there was a very important one discovered. We didn't see any in the ultra deep field. None that were very important. I mean, there are different kinds of supernova. We didn't see any that were useful for cosmology. But there were some parallel experiments with Hubble to take fields that weren't as deep but much wider to search for those supernovae. And one was called the GOODS. It stands for Great Observatories Origins Deep Survey. Actually, it was a group of people I hired, including Adam Riess. And originally, they came to me with a proposal. They said, we want to do the Great Observatories Deep Survey. And I said, you're going to have to watch your acronym control. That's not coming out of this institute, because we're going to be in trouble. So we added the origins part of it to make it a little bit better. That's a true story, by the way. One of my, as an administrator, I have to worry about the press. And that one actually pulled out a whole bunch of supernovae at high redshift, because what Hubble is unique for is we can see supernovae beyond a redshift of 1. You can't do that from the ground. It's impossible. And this turnover, I took the slide off, but really beyond a redshift of 1, you actually show this turnover going back to the original Hubble law. And it was very important to establish that. And we did that with Hubble in around 2004, 2005. And it was a beautiful series of experiments. So that was good.
Yes, this is kind of a pedestrian question, but I had always thought that the cosmic microwave background came from about the time that the universe became transparent. Did I understand you to say it was after that?
No, that's a good way to think of it. I mean, before that, what happened is if you have protons and electrons in a plasma, right, it's all ionized. Photons can't travel very far.
That's right.
And so that we call that opaque. I mean, it's not quite opaque, but as soon as the electrons and the protons combine to make hydrogen atoms, they don't interact with most of the photons. The photons just stream through without doing anything. And we call that transparent. So exactly that time when the electrons and the protons recombined and emitted what we see as the cosmic background, the universe became transparent, which means the cosmic background propagated freely until today, and that's why we can measure.
Okay,
before that, it was opaque because the photons and the matter were in constant communication.
Okay, thank you very much.
Yeah.
So the noise, of the stars around that line or galaxies around that line, is there some science in that, or is it instrument noise?
Oh, you mean the variations?
Yeah.
Yeah, it's a good question. We don't know if there's science beyond it, because right now that's probably noise in the measurements. But as we learn more about most of that noise is not the actual measurements. That is, we can measure things with great precision, but the problem is to put a distance out there, you have to know an intrinsic luminosity. And we don't know that well. There's some variation in the supernova luminosity, and that's what the uncertainties are meant to reflect. Now, if at some future time we find a way to calibrate better so that we know the luminosity and reduce that noise, there might be structure in there which is interesting. But right now we don't think that. We think it's just noise.
Given what we understand about the currently now about the large-scale structure of the visible universe, I'm wondering, do we know anything more about the great attractor and like when we might be getting there?
Oh yeah, well this is alluding to something else. So for the audience, I showed you these pictures where you get clumps of galaxies, and then you get kind of stringy parts of galaxies and voids. Well, the voids are actually surrounded by walls of galaxies. You're only seeing a slice, but they're really walls. And what we found, incidentally, when I say we, I did almost none of this. I just sit back and give the lectures. I mean, this is really my colleagues who are doing the work. But what we found, we astronomers found, and this is probably about, maybe as much as 20 years ago, certainly 15 years ago, is that by measuring the motions of the local galaxies and even some of the clusters of galaxies like the Virgo cluster, there's a great streaming in one direction more than in another direction. That is, it's not completely random. And the streaming, we believe, comes about because there's this huge mass of matter which has been deemed the great attractor. That's pretty local on the scales I'm talking about. So, that great attractor is kind of in scales which is down in the lower part of this curve in the sense of distance. So it's not way out there. But it's pretty massive, whatever it is. And most of it, of course, is dark matter. And so that's what the great attractor is.
Since the universe is expanding and it's expanding faster, is it the universe like a balloon, and at some point it'll pop?
Hey, that's good. Yeah. Well, I'm not sure it will really pop, because pop suggests there's something it pops into, right? I mean, if you have a balloon and you prick it, the air pops because it comes out of the balloon to here. And the universe is everything. So it doesn't really have anywhere to go. But what it would do as it's accelerating is the things that are now kind of fairly close together will get further and further apart until eventually they don't see anything. And so all of the matter kind of gets rarer, less dense, and eventually it gets dimmer and all the stars wind down and burn out. So right now, the prediction for the end of the universe is not that great. You know, we all just kind of wind down and it slows down, and it doesn't slow down, but it gets cold and there's nothing more. I somehow don't think that's going to happen. I mean, I somehow just don't. I think we just don't get it. We don't understand what happens next. All we're doing is looking at this part of the story. So, I for one will be fascinated just by the next young scientist who comes up and figures out that that's not it, but it's something else. So that's what we think.
So my understanding, when you use the term event horizon in the context tonight, my understanding is that we can see things up to the event horizon, but not beyond it.
Right.
And I'm just trying to understand what that really means.
Oh, so that means that the universe is 13.7 billion years old, you know, plus or minus 0.12, which is pretty impressive precision. And so light can travel a certain distance in 13.7 billion years. So we can't see anything that's farther than that away. That's the event horizon. It's just the age of the universe times the speed of light, translated by relativity into some distance. But, you know, that's all it is. It's that. So that is the event horizon. Any events that were occurring somewhere beyond that are outside of what is called our light cone. We heard that from an earlier questioner. And the light cone is just a relativistic way of saying what we're in communication with sometime in the past. And so that's all the event horizon is.
Okay. So purely distance and the speed of light. I had heard that acceleration, the relative acceleration, plays a role as well.
Well, yeah. So it's a little more complicated because it was going slower in the past. So I've given you the linear version that's easy. Sure. The real version, you have to get out a rather complex general relativistic calculation. It's actually called, this is a subset of what's called a Friedmann-Walker universe. And if you put all these constants in, it's not that hard, really. I mean, we've got plenty of engineers in the audience. You fire up Mathematica, 5 minutes, you're going to have the answer. But, you know, it's just not a linear thing. It's a much more complicated thing involving integrals over time. And so it's a mess. But it is one-to-one and easy to plot. And all it does is it takes a plot like this on a log scale. Instead of being strictly linear, there's some curve in there that you have to calculate. It's not a big curve, though, so it's not that hard.
My question has to do with the dark ages before 700 million ABB.
Yeah, and by the way, that 700 million is a little uncertain. It may have been dark. And we may go back a little further and still see stuff.
That's the age of the little red galaxies.
Yeah, well, the red galaxies are about 700 million years, and we still see stuff. So probably there's stuff even farther back than that.
Yeah, between 300,000 and 700 million or thereabouts, this dark age, were there stars that were not associated with the galaxy, or did the star formation only begin in galaxy-sized structures?
No, well, we don't know. The conventional wisdom is that that the formation of structure was a bottoms-up hierarchy. That is, little stuff formed before the big stuff. You formed a lot of little stuff. It kind of clumped up and made bigger stuff. So you didn't form galaxies first. Now, of course, the gravity acting at large scales was accumulating clusters of matter and cluster of galaxy-type scales while this little stuff was happening. And eventually, that was what allowed a lot of the little stuff to get together into not just galaxies, but then galaxies which collided, okay? But we believe that basically the stars came first, and then the galaxies, and then the clusters of galaxies. And some of the big clusters are still kind of forming. That is, in the age of the universe, they still haven't had a chance to completely settle down. They're still in the non-random motion part of their phase. And that's kind of interesting because you can measure it. But we can't completely confirm that. So and there are very reputable people who believe that maybe there were a few stars that formed in the early parts of these dark ages. And in principle, we could observe those. They're probably pretty faint. It's just not according to very conventional wisdom. It would require another way of looking at this is there is the stars and galaxies form from clumps, peaks in the density distribution of matter. Over the whole universe, some of those peaks were probably pretty huge. And the really big ones could have formed some stars very early on. And then the less peaky ones had a little bit longer to wait because it waited till they clumped up. So we just don't know. I mean, it's a power law spectrum, and it has to cut off somewhere on both sides. Otherwise, you get infinities, right? So there has to be what's called an inner scale and an outer scale. And there are ideas about what the inner scale is. I think the outer scale is set pretty easily by acoustic distances in the universe. But I think the inner scale, I'm not sure that we know, and to some extent, it's probably amenable to test when we get some new telescopes. So we'll see.
Thanks for watching. Please subscribe and don't miss out on new videos and lectures.